What if the smartest AI in the world confidently gave you an answer that was completely wrong? That's the problem with a language model working alone. It's brilliant, but it's frozen in time and it has no idea what's true right now. Today, we're fixing that. This is Retrieval-Augmented Generation, the architecture that gives AI a memory, a source of truth, and a way to actually look things up before it speaks. Let's break it down.
To understand why RAG matters, we first have to understand the problem it solves. And it comes down to three big limitations of a language model working in isolation. The first is that it's frozen in time. A model relies strictly on a knowledge cutoff date. Everything it learned stopped at that moment. It knows nothing about events from last week, yesterday, or 5 minutes ago. The second problem is data isolation. A standard model has zero visibility into private information. Your company's internal database, your proprietary codebase, your internal policy wiki, all invisible to it. It lives in a walled garden. And the third, the most dangerous one, is the hallucination risk. Without anything to ground it in facts, a model will confidently make things up. Ask it which planet has the most moons, and it might insist it's Jupiter with 88 based on outdated training, completely missing that Saturn now leads with 146. It's not lying on purpose. It simply has no way to check.
So how do we fix all of this? Think of it like the difference between a closed book and an open book exam. On the left, we have static generation. This is the isolated model answering purely from memory, from its pre-trained parameters. It's fast, but there's a high risk the answer is outdated or fabricated. On the right, we have retrieval-augmented generation. Before the system answers, it dynamically goes and retrieves up-to-date, specific, and private facts. Then it generates its answer grounded in that real information. That's the entire philosophy of RAG in one image. Don't force the model to memorize everything. Just let it look things up before it responds. Now, RAG isn't the only way to give a model new information. There are three main approaches, and it's worth knowing when each one fits. The first is long context, the brute force method. You just shove everything into the prompt. But this gets expensive and slow. And when you cram in 1 million tokens, the model struggles to find the needle in the haystack. It's best for summarizing a single, bounded document. The second is fine-tuning. Here you actually retrain the model on new data. Inference is fast afterward, but the training cost is enormous, and it's terrible for facts that change, because updating anything means retraining all over again. Fine-tuning is really about teaching a model a specific tone, style, or language, not fresh facts. And the third is RAG, dynamic retrieval. Low latency, cost efficient, and it updates instantly without any retraining. This is the winner when you need to search across huge amounts of constantly changing enterprise data. Each tool has its place, but for dynamic knowledge, RAG is the clear answer. Let's look under the hood. ARAG system really has two pipelines. The first is the ingestion pipeline, and this happens offline, ahead of time. You start with your raw documents, all your unstructured enterprise data. A chunking engine breaks that text into smaller, manageable segments. An embedding model then converts each chunk into numerical vectors. And those vectors get stored in a vector database, ready for fast similarity search. The second is the retrieval and generation pipeline, and this runs live at the moment a user asks a question. The user query comes in and gets converted into a vector by that same embedding model. A semantic search then pulls the most relevant chunks out of the vector database. Those chunks get combined with the original question. That's the augmented prompt assembly. And finally, the model reads all of it and produces an informed, grounded response. Two pipelines. One prepares the knowledge, the other uses it. Keep that mental model, because now we're going to walk through each piece in detail. Let's start with chunking, because this is where a lot of RAG systems quietly succeed or fail. Imagine feeding an entire 50-page employee handbook into the system for a simple question about remote work. You'd overwhelm it with irrelevant noise. So documents have to be broken down into smaller pieces. The common approach is fixed size chunking. splitting text into precise blocks of a couple hundred characters. But there's a trap. If you cut blindly, you might split a sentence right down the middle. Dogs are allowed ends up in one chunk, and on Fridays ends up in another. The meaning is destroyed. That's why we use the overlap imperative. By letting each chunk share a small overlap, say 50 to 100 characters, with the next one, you preserve the meaning across the boundary. Dogs are allowed on Fridays stays intact. It's a tiny detail, but it protects the semantic meaning of your entire knowledge base. Once we have our chunks, we need to turn language into something a computer can compare. This is the magic of embeddings. Models like all-mini-lm-l6-v2 take human language and convert it into a mathematical array, a vector. In this case, a 384-dimensional vector. Think of it as coordinates that capture the meaning of the text. And here's the beautiful part. Once meaning is turned into coordinates, we can measure how close two ideas are just using math. A dot product, a distance calculation. The shorter the distance between two vectors, the closer they are in meaning. Look at the space here. Dogs allowed in office and pet policy sit right next to each other. High semantic similarity. But remote work is far away, a vast mathematical distance from the others. The model never had to be told these things are related. It figured it out from the geometry of meaning. Now we hit a scaling problem. Comparing a single query against, say, 500 documents, each with 384 dimensions, means nearly 200,000 calculations per search. And that's a tiny data set. Brute force searching every vector one by one is completely unscalable. The solution is smart indexing. Algorithms like Hierarchical Navigable Small World, or HNSW. Instead of checking every single vector, the database pre-organizes them into interconnected semantic neighborhoods. The outcome is that when a query comes in, the system can instantly route it toward the right cluster, the right region of meaning, without ever scanning the entire database. It's the difference between reading every book in a library versus walking straight to the correct shelf. That's what makes retrieval fast enough to feel instant. Now let's talk about how retrieval actually finds the right information, because there are two very different philosophies here. On the left is keyword search, classic BM25. It ranks documents based on exact word frequency. It's precise but brittle. If a user searches for allowance, but your document uses the word reimbursement, it fails completely. Same meaning, different words, no match. On the right is semantic search. This measures the similarity of the vector embeddings we just talked about. So it can retrieve documents about remote work even when the user typed work from home. It understands intent, not just the letters. So which do you use? In the enterprise, the answer is usually both. It's called hybrid search, fusing the exact match precision of keyword search with the intent matching power of semantic search. You get the best of both, and you eliminate the blind spots each one has on its own. We've retrieved the right information. Now comes the final step, actually generating the answer. And this is where the grounding happens. The formula is simple. You take the user's original query, plus the retrieved vector chunks, plus a set of system prompt instructions. Combine all three, and you get a grounded response. Two things make this work. First, the assembly. The highly relevant chunks are injected directly into the model's context window, right alongside the original question. And second, the constraint. The model is strictly instructed to build its answer only from that injected context, not from its own memory. That constraint is the secret weapon. By forcing the model to answer only from the facts you handed it, you virtually eliminate the hallucination risk we saw at the very beginning. The model stops guessing and starts citing. Now everything we've built so far is what we call naive RAG. And it's powerful, but it's not perfect. As you push it into the real world, three cracks start to show. The first is context loss. A basic system treats every query as an isolated event. It instantly forgets the conversation you were just having, so follow-up questions fall apart. The second is vocabulary mismatch. Sometimes the user's short question just doesn't mathematically line up with the dense technical language in your documents, so the right answer never surfaces. And the third is irrelevant retrieval. The system fetches documents that technically match the query, but the content itself is low quality or unhelpful. These aren't reasons to abandon RAG, they're the reasons RAG evolves, from naive to advanced to agentic. Let's climb that staircase. Here are 3 upgrades that turn naive RAG into something far more capable. The first is HYDE, hypothetical document encoding. Instead of searching with the user's raw query, the model first generates a hypothetical ideal answer. Then it searches the vector space using that answer. Because a full answer looks a lot more like your documents than a short question does, you get dramatically better semantic alignment. The second is RAG with memory. This adds a conversational history layer so the system remembers what came before. It transforms isolated single-shot queries into a continuous context-aware reasoning thread. Now follow-up questions actually work. And the third is adaptive routing. A lightweight classifier looks at each query and decides how to handle it. Does this need a simple vector search, a complex multi-step search, or no retrieval at all? If someone asks what's 2 plus 2, there's no reason to go digging through a database. The system routes intelligently. The next leap is teaching the system to check its own work. 2 architectures lead the way. The first is corrective RAG, or CRAG. It introduces a rigorous quality gate after retrieval. Every retrieved chunk gets scored. If it passes the confidence threshold, it's routed to the model. But if it scores too low, the system automatically falls back to a web search to find accurate data instead. It refuses to build an answer on weak evidence. The second is self-RAG. Here the model generates internal reflection tokens in real time. As it writes, it continuously critiques itself, asking, is this specific claim actually supported by the retrieved context? If not, it corrects course on the spot. Together, these turn RAG from a system that just retrieves and hopes into a system that verifies, reflects, and self-corrects. And this brings us to the cutting edge, where RAG stops being a pipeline and starts becoming an autonomous reasoning engine. The first frontier is agentic RAG. Here, an orchestrator node sits at the center and decomposes complex multi-part queries. Ask it to analyze the 2025 gold price hike and compare it with other metals. And it decides which tools to use, the vector database, a calculator API, a web search, and it loops through them until the answer is fully synthesized. It doesn't just retrieve, it reasons and acts. The second frontier is graph RAG. Instead of treating documents as isolated chunks, it maps the explicit relationships between entities. Vendor A affects regulation X, which governs contract B. Because the connections are modeled directly, the system can instantly answer complex relational questions like, how does this new regulation affect specific vendors? That's reasoning across an entire web of knowledge. So let's bring it all together because this diagram is the whole journey in one view. The foundation is this. RAG cures the fundamental paradox of language models. It transforms isolated, forgetful systems into dynamic engines grounded in private, virtually infinite enterprise reality. The evolution is how it scales. Simple vector search grows into hybrid search, into query expansion with techniques like hide, into self-correction, rising to meet rigorous, real-world enterprise demands. And the apex, the future, belongs to orchestrating autonomous AI agents operating over complex knowledge graphs. A system that doesn't just answer questions, but continuously learns. A true digital nervous system for modern AI. That's Retrieval-Augmented Generation, from a single grounded answer all the way to autonomous intelligence.